Today I'll continue the discussion on semiconductor lasers and obtain the oscillation condition for obtaining laser output. Last lecture I talked about population inversion. Today I will talk about the conditions, including optical feedback, which enables one to get laser coherent light output from a semiconductor laser. At the beginning of the last lecture, I talked about the enormous improvements that have taken place in the field of semiconductor lasers. So I'll just illustrate that by showing how, in going from homojunction lasers, the threshold current density in amperes per centimeter squared has come down with time, 1962, 72, 82, 92. The first homojunction lasers had threshold currents greater than, if I, this is 10 to the power 1, 10 to the power 2, 10 to the power 3, 10 to the power 4, 10 to the power 5 amps per centimeter squared. Enormous span, 5 orders of magnitude. The first homojunction lasers had threshold currents of the order of 10 to the power 5 amperes per centimeter, 100,000 amps per centimeter squared. Of course, the devices were very small, so that the actual currents were still of the order of 10 amps. So it was a high power device. For single heterojunctions, this in the mid 60s, we had a single heterojunction device there. Then we had a double heterojunction device somewhere there. And if I draw the final curve, it will look something like this. Then between 72 and 82, there were the multi-quantum well lasers. And finally, going up to 92, there was the quantum wire lasers, which had this figure 22 has been reduced to about 10. There has not been a dramatic improvement, but this is about 0.6 milliamps. So a laser such as this can be run off just pencil batteries. Okay? The current consumption is so low, the power dissipation is so low, that it becomes a very handy portable device. So you see that through the use of firstly heterojunction technology, then quantum wells, quantum wires, using microcavities, we've had a dramatic improvement in the performance of semiconductor lasers. So in order to understand that, we have to start off at the beginning, understanding the condition for semiconductor laser operation. The two conditions necessary for practical lasers which are fabricated nowadays are population inversion. This is what I discussed last time. And from the equations that I gave last time, it is possible to determine that the gain coefficient, G as a function of energy, which is just the negative of the optical absorption coefficient, is related to the h cubed c squared by 8 pi n bar squared e squared over R. This is from the Einstein relation relating the absorption to the stimulated emission. They are equal and opposite processes. So it should be possible for you to deduce this from what I derived last time. And we see that the gain, alpha we know is the optical absorption, the units are centimeter inverse. Okay, so gain is the opposite of optical absorption. It is also measured in centimeter inverse, and we'll see that, for example, if you have a semiconductor which is a passive material, okay, then if you plot alpha E against E, we know that depending upon the band gap of a semiconductor, we get some alphas like that. Okay, what we'll calculate later on is for different semiconductors. For a p-n junction, once you inject carriers, okay, then you find that the absorption is offset by and with increasing current one gets gain at particular frequencies, and from this it should be possible to calculate what is the threshold current and what is the wavelength at which the laser action takes place. Okay, so this is just to show that the gain is the negative of the optical absorption coefficient. The units are both centimeter inverse. If we take a practical structure, which is a cavity to provide optical feedback, we can look at a cavity of length L with mirrors providing reflection. Let us say that the reflection coefficients of the mirrors are R1 and R2, and the transmission coefficients are T1 and T2. This is the gain medium. This is a medium in which stimulated emission is taking place in the presence of photons. So let's assume that we have an incoming intensity EI, and we want to see under what condition this cavity sustains oscillations. Because remember, laser stands for light amplification using stimulated emission of radiation. Okay, so a laser is a coherent oscillator. Okay, and so we want to see the condition under which self-sustained oscillations are obtained. Regarding the mirrors, let's say that this is the input plane. Obviously, the mirrors will not be 100% reflectors because we want some light to come out finally. Let us say that the left mirror, this is the left mirror and this is the right mirror. Left mirror has a ratio of reflected to incident fields R1 exponential j theta 1, and here the reflection is, the output to input ratio is given by R2 exponential j theta 2 at the right mirror. so the actual reflection, power reflection coefficient, these are the reflection coefficients of the field. The ratio of the incident output to the input powers are given by obviously R1 into R1 complex conjugate, and similarly R2 is equal to R2 into R2 complex conjugate. And if we neglect these thetas, we neglect the phase changes, so this is equal to, you can say this is R1 squared, and this is equal to R2 squared. So the small r1s are the reflection coefficients of the electric field, and capital R1 is the reflection coefficient for the incident power. Okay. Now here let us say this gain medium has a propagation constant gamma. Okay. And we want to see what happens as the ray traverses this cavity from left to right. Okay. Let's say that the input at the left-hand plane the electric field incident electric field is EI, so EX as a function of Z and T is equal to EI exponential minus gamma Z, and it's a sinusoidal field exponential J omega T. So this is the propagating in the Z direction. We're taking a one-dimensional case. So at the first mirror, we have a transmitted field EX, which is T1 into EI inside the left boundary, okay, at Z equal to 0. And on the right hand side at Z is equal to L, what do we have? That the electric magnitude of the electric field, we are omitting this for simplicity, the sinusoidal variation, we're looking at the spatial variation. This will be T1 EI. Okay, so this is EI over here. This is T1 into EI. Okay, because only T1 portion is transmitted through the mirror. Then this propagates. It goes through a length L, so when it reaches this point, it is T1 EI into e to the power minus gamma L, okay, at this point. Where gamma is obviously a complex propagation constant. This is at the right mirror.
Propagation constant is related to gain coefficient.
Propagation constant will be proportional to the gain as well as the loss. Okay, difference between the gain and the loss.
Right. Negative because due to gain.
No, but we are right now not talking about gain. We are talking about gamma is something minus alpha x. Okay, it's minus alpha z. We are saying that this will be it will be positive if there is gain. It is negative if there is loss. Okay. Now what happens here? We are interested in the light reflected back into the cavity. Here the reflection coefficient is R2 at the right hand mirror. So we can see that obviously this at right mirror the reflected beam has the intensity Ex equal to T1 R2 EI exponential minus gamma L. Okay. And so this will continue, and finally, after a number of such reflections, we are looking at what will be the transmitted beam here. Okay. So the amount reflected is T1 R2. The first part that is transmitted here, okay, this part that is transmitted here will be T1 EI e to the power minus gamma L into T2. Okay. First part that is transmitted is T1 into T2. So the first component of the transmitted beam will be T1 T2 EI exponential minus gamma L. Okay. Okay. Now you can see quite easily that there will be successive transmitted beams. This beam will be reflected. It will be reflected here, come back, and there's a path length of twice L. So the next beam will have, the first transmitted beam will be just this, plus R1, R2 exponential minus twice gamma L, okay, plus again R1 squared, R2 squared exponential minus 4 gamma L, plus etc. Okay, so this is the first one, T1, T2. Then this beam will come back here. Okay, it'll be reflected here, T1, and then it'll be reflected here will be R1 into R1. Okay, and then the amount reflected here is R2, here R1, and it'll be transmitted again. Okay, so each time it undergoes reflection, it'll be R1, R2 into e to the power minus twice gamma L. Okay, is that clear? So the overall intensity, transmitted intensity, will be given by this series, and if you look at the series, you can see that it can be summed up. ET is just EI. In the numerator, it will be T1, T2 exponential minus gamma L. And it's a geometric progression, so it will be 1 minus R1, R2 exponential minus twice gamma L. Okay, this is the summing up of the total transmitted. So we are looking at after successive traversal of the medium. Obviously, if the medium does not have any gain, then obviously it will be gamma will be equal to alpha and it will be attenuated. Okay. Now, a laser is a self-sustained oscillator. Okay, and so the condition for self-sustained oscillations, okay, if there is a certain amount of gain, then with EI you will get something ET. But suppose if it's an oscillator, you don't need EI, right? You don't need any incident energy. And what is the condition when it will break into oscillations? We know that an amplifier, if you remember electronics, an amplifier with feedback, if the feedback 1 minus A beta is equal to 0, or A equal to 1 by beta, okay, then you get oscillations. An amplifier will, with positive feedback, will start oscillating. So it's exactly similar. So the condition for oscillations is that 1 is equal to R1, R2 exponential. The denominator is equal to 0, so 1 minus twice gamma L. Okay. And what is gamma? Gamma is related to the real and imaginary parts of the refractive index. K is the extinction coefficient into K0, with K0 is equal to just 2 pi by lambda 0, where n is equal to n minus j k star is the complex refractive index. If k is equal to 0, okay, this k, j into j, k gives a real term, so that gives loss. Whereas if this n is the refractive index, which just gives the phase shift. Okay, so in this case, what is k bar? K bar is just alpha. From right at the beginning of the definition of extinction coefficient, k bar is just alpha lambda 0 by 4 pi. This is the extinction coefficient. Okay. So if we substitute the value of gamma into this, then we find that that equation becomes R1 R2 exponential G minus alpha I into L, okay, into exponential minus twice J 2 pi n bar by lambda 0 to L is equal to 1. This is saying that here for alpha we are putting G minus alpha, okay, where the G is the possible gain. This is the real part, and this is the imaginary part, which just gives the phase shift. So now if we look at the two parts, the real and imaginary parts, we get the condition for oscillations. There is a amplitude term and there's a phase term. The first part gives the amplitude term. The amplitude term there must be enough feedback. So G minus alpha I into L. Alpha I is, there are various types of absorption, so this is the ith coefficient of absorption, must be equal to 1. Okay. So if you take the logs and rewrite it, the condition becomes G is equal to alpha I, okay, and you take L the other side, so you have plus 1 by L log 1 by R1. These are the reflection coefficients. So this is the amplitude condition for laser oscillations. And it's easy to understand this. This is just the loss. This is the gain. So the gain must be obviously greater than the loss. And what is this? Okay. This is the mirror loss. Because if this is 1, if this is 1, okay, then this term vanishes. And why is it 1 by L? Because this is, if you multiply it through by L, G L into alpha L, this is independent of distance, okay? So this is the mirror loss term. And if we make this 90, 95, 99%, this will give you a small term. So obviously in an oscillator, the gain must be enough to offset the losses. This is the absorption in the medium in the length L, and these are the losses at the end of the mirror. Okay. If you go back to this cavity diagram, okay, so when the wave is propagating here, if you have enough electrons in the higher state, okay, then when the wave is propagating, okay, you will get some absorption and you will also get some stimulated emission. The stimulated emission is giving you gain, okay, and this is giving you absorption. So over this path length, okay, this gain must be enough to offset not only this absorption here, but it must be enough to offset the losses at the mirrors. And how does gain increase? Obviously, if you pump, for example, if you increase the current, okay, if you increase the current, then the excess carriers delta N, delta P are increasing. Delta N, delta P increasing means that there's more recombination. If there's more electrons in the upper state, more holes in the bottom state, okay, with increasing current, then obviously this will increase and G will increase. So obviously there will be some threshold current beyond which it will start lasing. Okay. Now, for example, right now there is a lot of work going on. Suppose you make this laser medium very small, then suppose you can reduce alpha, okay, then you can reduce the threshold. So there is a lot of work on microcavity lasers, trying to reduce this alpha. What is this alpha due to? Alpha, even in a semiconductor, okay, this is a PN junction, there will be some free carrier absorption. Okay. If there are impurities, there could be some impurity absorption. If this thing is very small, there can be some diffraction losses. Okay, the light may be lost due to scattering. If there's any inhomogeneity, there can be. So there are a number of loss mechanisms that I'll discuss later. Okay, we have just examined this part of the expression. That is, the feedback, the amplitude of the feedback must be enough, the gain must be enough to offset the losses. What is the phase condition? The phase condition is connected with this. The feedback must be in phase. It's coherent oscillation. Okay, so the feedback must be in phase. So the phase condition is that, okay, this 4 pi n bar by L0 L must be some 2m pi. So it is just 4 pi n bar L by lambda 0 is equal to twice m pi, where m is equal to 1, 2, 3, etc., integer. So essentially, okay, if you just cancel it comes down to n is the refractive index. This is the wavelength in the medium. Okay, m wavelength in the medium must be equal to some integral number of the wavelength in the medium must be equal to twice L. The path, total path, optical path. Okay, so this is the other important condition. This is the phase condition. And suppose we have different modes, depending upon m, we can say that we can have, suppose we rewrite this m lambda 0 is twice n bar L. Okay, this is the effective path in the medium. So this is the same condition. So if we have, here's the cavity, okay, we can have one mode, okay, in which this sort of thing. We can have another mode going like that. Okay. This is the electric field distribution within the cavity to give you the phase condition. So these are what are known as different longitudinal modes, depending upon the value of m, which will give you the correct phase relation, and we can find out what is the modes, what will be the mode spacing, difference in wavelength between different modes. Now we wrote m lambda 0 is equal to twice n bar L. Let's examine this and differentiate. Lambda 0 dm plus m d lambda 0 is twice L dn bar. So what is this? Is dispersion. The refractive index is not constant independent of wavelength. There will be some variation of refractive index with wavelength. That is a property of the medium. So for adjacent modes, dm is equal to -1. Okay, and then we can write that d lambda 0 is equal to lambda 0 squared twice n bar L. It follows from this and this expression, 1 minus lambda 0 by n bar. So this is what gives you the spacing between adjacent longitudinal modes. One can work out a numerical example. N bar is known, dn bar d lambda 0 is known for a particular material. Length of the cavity is typically a few hundred microns. Lambda 0 for fiber optic devices are typically, a micron or so, and this d lambda 0 comes out to be of the order of a few nanometers, typically a few nanometers. So this is an important result, giving you the longitudinal mode spacing, which comes from the phase condition. The gain. Let's go back to the gain condition. We got the gain condition 1 by L log R1 R2, but remember R is equal to R1 squared, R1 R2 is equal to R2 squared. Okay, so if you substitute that, then you get G is equal to alpha I plus 1 by 2L log 1 by, these are the power reflection coefficients, and if you have R1 is almost equal to R2, then you have a simplified equation, G is equal to alpha I plus here again this goes 1 by L. So this is a simple expression giving what is the gain, and one can say that at lasing we can then call this the threshold, GTH. Okay, threshold gain, which will be enough to overcome the losses. Next talk, I'll actually this is a very important expression which is really applicable for all types of lasers. But for semiconductor laser, one can go a little further to find out from this GTH what will be JTH, the threshold current density in amperes per centimeter squared. Okay. We'll derive that next time. If we look at certain values, what are the typical losses in, say, in a gallium arsenide laser? That determines the alphas. Alpha will be alpha free carrier. Remember when in absorption mechanisms of a semiconductor, I talked about free carrier absorption, which is within the band. For heavily doped materials, this is reasonably high. You cannot neglect it. And as you know, for PN junction semiconductor lasers, in order to get the population inversion condition, the materials are reasonably heavily doped, 10 to the power 17, 18. So there's, okay. Plus there is a term alpha diffraction. These devices are very small. Typically, the devices would be, let's say, this is a semiconductor laser. Okay, this may be the active region. Okay, this L. Okay, let's define L. Let's define. This is the width, and this is the thickness. Okay. Now, if we have an edge-emitting laser, which is the most common, this is where the PN junction and the light comes out from here. L is typically of the order of 250 to 400 microns. For conventional, not microcavity, W is typically of the order of about maybe 100 microns. And T, this is on a substrate. The substrate is thinned. T will again be of the order of about 120 to 150 microns. And okay, the way it's made, the substrate is here, and the light output comes out from this edge. Okay, like that. Now, if you want to reduce the current density, this is a typical edge emitting. Notice that the dimensions are nothing near as small as integrated circuits. We're talking about hundreds of microns. Okay, so integrated circuit technology has gone to 1 micron. Okay, here none of these dimensions are of that order, except that this well thickness, okay, this active layer thickness D. Well, this active layer thickness D, I'll show. These layers could be something of the order of about 0.1 to 0.2 microns. Okay. The growth takes place by liquid phase epitaxy or MOVP or MP. So the active layer thickness can be very small. Now, where does the current flow? The current comes there and it exits there. Okay. Now, you want to avoid the effect of the surfaces, okay, and you want to have a high current density, and I is J into A. Okay, what is the area in this? The area is this W into L, right? Okay, which is fairly large. So, in order to reduce this actual current and increase the current density, what is done is normally you have what is known as a stripe geometry laser. So the contact here is the whole. So this stripe geometry, let's call that say S. Okay, S is of the order of 7 to say 15 microns. Okay, so this requires photolithography, and what is the benefit of that? The benefit of that is that when you look at the laser front on, okay, say this is the substrate, okay, and the various layers, this is ohmic contact, etc., etc. This is the active region. D is say 0.2 microns, and the stripe geometry is, okay, this is exaggerated, it's only this much. Okay. So this is the metal contact, and this is the entire metal contact. So the current actually flows. This is important when we do calculations later on about the threshold current density. The current actually flows. If this is 100 microns, this is only 10 microns, so the current lines flow. Okay, like that. And the actual region which is emitting is only an aperture, a rectangular aperture like that. Okay. The advantage of that is that you are, overcupping. You're not having current. The surface. Okay, you can, you can coat the surface. You can, make it passive, etc. But the current does not flow. So surface recombination does not play a role. How do you achieve this? How do you have ohmic contact just there? Well, there are various ways of doing it. You can, for example, have an oxide. Okay. So that this is a metal and the rest of it is an oxide. So even if you have a contact, like that, okay. This is an insulator. Okay. So there is no current flowing. So this is called what is known as a stripe geometry laser. And this is what we'll use for calculations of JTH. Now to go back to our calculation, GTH was alpha plus 1 by L log 1 by R. Alpha was, we can say this roughly about 20 centimeter inverse, 1 by L 400 microns, so 1.04, and log, say R is 0.3. Okay, so you can work this out. 20 plus 25. Log, say 3.3. This comes to typically something of the order of 50 centimeter inverse. Okay. So the threshold gain has to be more than about 50 centimeter inverse in order to get lasing action. Of course, you can reduce this. Suppose you increase R, you reduce alpha, then threshold, this GTH can come down to a few centimeter inverse. So today what we've seen is fundamentals of laser action, which is described by there's a gain condition giving a threshold gain and the phase condition, which shows that there must be an integral number of wavelengths in the laser cavity, and as I've shown, this is W, okay, and this is T.